Electric fields can sound and seem really weird, but electric charges are all around us. All you need to do to see them is just take a plastic rod and rub it against some wool. In this case, electrons will leave the wool and jump onto the rod. The rod will get a negative charge. The wool will be left with a positive charge. And that charged rod can do some interesting things. Some really interesting things. And note that we're not creating any charges, we're just separating them. Also note that there are two different types of charges, positive and negative. Like charges repel, opposite charges attract, and the force of that attraction is given by Coulomb's law. Force is equal to K, that's a constant, times charge 1 times charge 2 divided by the distance between them squared, which might remind you of Newton's law of universal gravitation. It's an inverse square law, so let's try to use it. Let's try to show these charges doing stuff with pith balls, which aren't really that complicated. You just take that charged rod we've talked about, rubbed it against some wool there, and you bring it near this neutral ball. Wow! Something's happening already. I thought you said that ball was neutral, and yes, it is. Count them. 1, 2, 3 positive charges, and 1, 2, 3 negative charges. Overall, that ball is neutral. But the charges have been organized. Those positive charges are attracted to that negatively charged rod. They've migrated to the left. The negative charges are repelled. They've migrated to the right. And here's what makes the magic happen. The inverse square law says that closer is stronger, so the attraction from the positive is stronger than the repulsion from the negative, but don't get too close. Yikes! You know what will happen if you get too close? You'll have charge by conduction. And then the negatively charged pith ball will be repelled by the negatively charged rod. It would also be repelled by another pith ball charged in the same way. However, it would be attracted to a different type of rod. Anyway, let's get back to normal. What did we do there? We grounded the pith ball. How'd you do that? All you needed to do was touch it. You touched it, and those negative charges ran off the pith ball. Those excess negative charges ran off the pith ball. So now you could say that there's no charge on the pith ball. Well, you can't really say that. You could say that the ball is neutral, meaning it's got the same number of positive and negative charges, but charges are in all matter. So we can't say that they aren't there anyway. Once again, we have charge by induction. That's an attraction charged without touching. But now let's touch it with our hand. And now we're grounding it. We're allowing those negative charges to run off the pith ball. Those negative charges didn't like being there anyway. So after the hand is removed, we're left with a positively charged pith ball, one that would be attracted to that negatively charged rod. Well, I think that's really cool. You gave the pith ball a positive charge with a negatively charged rod because we have two different types of charges. But here's the bigger question as far as I'm concerned. How do they even know about the other one? How does that pith ball know that there's a rod near it that it should be attracted to or repelled from? Well, the answer is the electric field which surrounds all charges. And when I say field, you should think force, because that's what an electric field does. E, the electric field, is equal to the force per charge. A force is equal to the strength of the electric field times the charge in that field. Charges create fields, and fields put forces on charges. Notice that the field lines point away from the positive point charge, and the field lines point towards the negative point charge. The direction of the field line shows the direction of the force on a positive test charge. The density of the field line shows the strength of the field. So here again we have the inverse square law. The closer you are to the charge, the stronger the field. Here are two positive charges repelling one another. Their field lines push against one another, but they never cross. Here we have opposite charges attracting one another. The most useful field is the field between the parallel plates of a parallel plate capacitor. We'll say much more about a parallel plate capacitor. That's the most uniform, the most useful field. Notice those parallel lines, those equal density lines. That's the most useful field. It's not the most exciting. That probably comes from the Van de Graaff generator. Here are some clips of Van de Graaff generators doing crazy things here, putting charges on bubbles, and the bubbles float away, and then we even have it lighting up a fluorescent light bulb. But the classic experiment involves making somebody's hair stand up. Now, why does the hair stand up? Well, let's take a mannequin head like this and put it on the Van de Graaff generator, and the hair stands up because the hair doesn't like itself anymore. The hair doesn't like it. Those hairs all have charges on them, and the charges don't like each other. They repel one another. That hair is trying to get as far away from itself as it can, which it can when somebody provides a path off the hair. A spark, a lightning bolt, an electrified path through the air. Something I bet you've experienced yourself. Here we have the gaining of some excess charge and the discharging of some excess charge. And if all of this seems a little overly conceptual, we can use these ideas of fields and forces to peer down inside the atom and to measure the charge of an electron. This is the Millikan oil drop experiment. Here we have a parallel plate, another parallel plate capacitor with an electric field between the plates. We will spray in some oil droplets. One of those droplets will find its way between the plates, and then by adjusting the strength of the field, we can get a drop to float. Blast it with x-rays. That's kind of like rubbing it. Blasting it with x-rays gives it a charge. Now you have a charged particle inside an electric field, and you can levitate that oil drop. Levitating oil drops. Now I've heard of everything. We have a free body diagram here. We have an electric force up and the gravitational force down. The weight force, mass times 9.8, that's the weight force. It's the charge of the drop times the strength of the electric field. That's the upward force. And if you can get these two forces to balance, as Millikan did, and you know the mass of the oil droplet based on its size, you can view it with a microscope, you can find the charge of an electron as we begin to peer inside the atom.